Welcome to our parallel programming concepts course. Today we are going to talk about accelerators, and in this lecture we talk about accelerator technology. So how are those systems built and what are their special features? First of all, we already learned about SIMD, single instruction multiple data execution, one of Flint's hardware taxonomies. And most of the modern accelerators are actually built in this way. So we have one instruction that works on multiple data in parallel. Why is SIMD a good idea for accelerators? Or where does it come from that accelerators actually use this? And here we have to look at the past of one of the most famous accelerators, and one of the most famous accelerators were GPUs. And in the past, like in the 80s and 90s, GPUs were used for one particular task, for rendering graphics. And this was so fixed that they actually built everything in hardware, and there was no way to program this or to tweak this. Okay, so this is called fixed function graphics pipeline, and the case is actually that everything is fixed, and then people wanted to have cooler graphics and something that's more individual for games, for example, and they came up with programmable real-time graphics, where you had APIs in order to create some shaders that tweaked the vertex processing in a way, and pixel shading was also added, and you got access to textures and could do something with the textures, like, for example, making the edges a little bit stronger or making it a little bit more reddish or something like this. And then in 2006, NVIDIA came up with a new model where they unified those shading stages and allowed them to be really programmable. And what this actually means is what we are going to look like now. So before 2006, we had the hardware looked like this. So we had a vertex shader, and then we had the pixel shader, and the data was going into the vertex shader, and the result data was going into the pixel shader, and these were actually parts of the hardware. And then with DirectX 10, there was a new shader that people came up with, and this was the geometry shader. So now we had the vertex shader, and the results were going into the geometry shader, and those results were going into the pixel shader then. And then NVIDIA thought, oh well, if we want to put that into our card, we need more space, because we have now an additional processor doing this geometry shading. And if we need additional space, we have bigger cards, and bigger cards are like bigger and more expensive, and then some of their clever engineers came up with a different solution, and the different solution was to, instead of add a new hardware part, was to consolidate the parts that they already had. And they came up with this. And instead of having vertex shader and pixel shader, they now have one shader that's programmable, and you put the data into it, and then you do the vertex calculation, and then the results are flowing back into it, and you do the geometry calculation, and then the results are flowing back into it, and you do the pixel calculation. So you configure it 3 times, and then you just run the data 3 times through it. The cool thing here is that you could now have smaller cards, because this unit was even smaller than vertex and pixel shader and geometry shader together. And or alternative to this, you could have more compute power, because you could use all the space to put all the transistors into this very unit and make this very strong. Okay, so this is what they did, and now this shader was programmable. So you could really do some cool calculations there, because they needed this in order to make sure that it supports vertex, geometry, and pixel operations. And then this was the basis for a way of programming or using GPUs that was called general purpose GPU, where you computed problems, you used compute problems and then used graphical operations on those, and as a result you had everything in textures basically. So we see a small example here. Let's say this is a scientist, and the scientist has data on the left-hand side and a formula that it wants to use on the data, and then he wants to have a result. And in this example, he looks for all the values that are larger than the average of the values. So with those new GPUs, since they were programmable, he could have the idea that, oh well, this system is super fast. I'm going to use this for my calculations. And what he was doing then was to put the data into a texture. And as we see in the texture, each of the numbers has a color, and higher numbers are darker in this part. So he created a texture because the GPU is only understanding textures. And then he put his data as a texture onto the GPU. Then he created a shader out of this formula. Whereas the GPU saw this was actually a GPU shader that was used to enhance the texture in a way by working on the texture. And what actually this mathematical formula was then executed as a shader on the GPU, on the texture. The result was a texture again. And then he had to look at the result texture and have this interpreted as result data in the end. So this was the way that people were using the GPUs because they were so super fast. We've seen the hockey stick picture in the last part of this lecture, and this hockey stick was actually the reason why people started doing this, because they could get like 10 or 100% faster calculations on the GPUs for the tasks that were expressible on GPUs. But the set was very reduced because they were not intended to do all the stuff. But then NVIDIA figured out that people were doing this actually, and a lot of researchers did this, and they had a number of success stories. And they thought, oh well, if people are doing this anyway, maybe we could make it easier for them. And they created a new programming model that is called CUDA, and made those shaders fully programmable in C or in standard languages. And now you have, and they added some features that you would need in order to have a real programming languages, like load and store destruction, barriers, and atomics that we've discussed already in other parts of our lecture. And the era of GPU computing was born. So in the past, we had fixed function. Then we had some small changes to make it programmable for having better optics and better graphics. And since NVIDIA unified this, we had a better way of programming this and a more powerful way of programming this. People use this with this GPGPU approach to express their calculational problems as shaders and run those on the GPUs, and the data was then expressed in textures. And NVIDIA thought that it might be a good idea to create a real programming model that people could use, and this is what we have today, GPU computing, where you actually can write C programs and run those on accelerators. Okay, so what's the big difference between GPUs or accelerators and CPUs? One difference we were already talking about. While CPUs can run different tasks that do different things, GPUs are only good at running a particular tasks on a multitude of data. So the same task again and again on a very large variety of data. So on the left-hand side, CPU-style task parallelism. On the right-hand side, GPU-style data parallelism. Why is this so? When we look at the underlying hardware, then we see that a lot of transistors on the CPU are used for the cache. This is due to the severe impact of the memory wall. Instead of waiting for the memory all the time, the CPU usually just has a small copy or a large copy of the data already and works with this copy. And since cache is way faster than the memory, this is a way to break the memory wall, kind of. And also, we have a big control unit where all those ILP mechanisms are implemented, for example, branch prediction. The CPU guesses what the right branch will be in the future and does some calculation in that direction, and only if it turns out to be false, it takes the other branch. But usually they are right, like in 95% of the cases or something. So they have a small number of very huge threads and this branch prediction. On the other hand, on the GPU, most of the transistors are used for actual computing devices. So all the yellow parts on the right side are processing elements again who do the calculations. And in addition, we have very small caches and a very small control unit. Why do we need a very small control unit only? Because GPUs don't allow for branching, for example. In a GPU, since every thread is exactly doing the same, they just have one instruction per execution processing element, and they also have just one program counter. So they really make sure in hardware that each thread is actually doing exactly the same. And the cache is very small as well, because they have another concept to deal with the memory wall, and this concept is having so many threads. Since they had thousands of threads, because for each of the pixels in the result image they had one thread, and since a picture is usually thousands times 1,000 pixels or something, they have really a large amount of threads. And they use all those threads in order to hide memory latency. When one thread starts accessing memory and waiting for it, then they just put those threads away, take other threads, and have those other threads running. And if those access memory again, then they take another subset of those threads and have them running, and so forth and so forth. And sometimes in the future, the memory requests will be responded to, and then they just have the threads running that were waiting for this. So they have a large amount of threads, and they just switch them around all the time. Here we see this again. GPUs are executing exactly the same instruction, the exact same line of code for all of the threads. Since they even share a program counter, branching is not allowed. If one thread is wanting to do something else than all the other threads, then they all do what those threads are doing first, and this thread is just not really doing it. He's doing the same operations, but he's not writing the results back. And afterwards, they do what he would like to do, and everybody is basically doing this, but they don't write the results back. So no branching, everybody is doing the same, but the results are written back sometimes and sometimes not, so that it looks like branching to us. The concept to deal with this memory wall here is to have memory latency hiding, where we have so many threads that we could always have runnable threads that are ready to do something. And we have some threads then running when others are waiting for the memory. And this actually means that we need to switch between threads very, very fast. And GPUs allow this because they don't implement a context switch like a CPU is doing it currently, where we had to store the whole state of the CPU and then loading a new state for the new thread. And we have to save all the registers, and we have to save the caches and something. We don't have this for GPU threads, because here we only save because here we don't need to save anything, because there are so many registers on the card already that it can hold 1,000 threads, and also threads are usually not using so many registers. So let's say we have thousands of those simple threads, and each of them would use 4 registers, then we would need 4,000 registers, and current GPUs have around 64,000 registers on the GPU already. So you really can store a lot of threads at the same time, and context switching, since they do not have a program counter and they are all at the same position, and since they share the cache anyway, all you would have to store would be the registers, and they are already there. You don't need to put them somewhere in the memory, because they are on the CPU already, on the GPU already. Okay, let's see what it looks like in real hardware. So this would be a GPU chip, and since this only looks like copper to me, we have a more schematic view of this. We see that this GPU architecture comes with some clusters. We have 4 clusters here and a big level 2 cache. This is new, so modern GPUs have a cache like CPUs as well, and this is only there for general purposes. So those GPUs wouldn't need this if they would still just do graphics, but they can very much benefit from this for those calculation tasks. So the GPU vendors added caches to their GPUs in order to make sure that they could be used for calculation tasks. Okay, so we have those 4 clusters, and in each of those clusters we have 4 symmetric multiprocessors. And symmetric multiprocessors are basically a processor, and each of those then has a number of scalar processors. Scalar processors are like cores in the CPU. Okay, so we have a big CPU, and we have lots of those CPUs, and we have lots of cores on each of those CPUs. And as you can see here, those are way more cores than we have on CPUs. Currently we have around 48 cores per GPU, CPU. Okay, and here we see that in addition to all those cores, we have a big register file, and we have some cache, and we also have a very small instruction cache. And we need so many registers because we need to store all those threads. We have a very small cache because we have memory latency hiding, and we don't rely so much on caching, but we have one cache for computational purposes because for some algorithms this is pretty cool. And you also can use this cache yourself. So in contrast to CPUs where the cache is all implemented in hardware and you have no influence on this, here you can configure your cache in a way that you get the vast amount of the cache to manage it yourself. And you can actually say what is going into the cache and what is happening with the cache. This is pretty cool and adds new possibilities for you as a programmer. And also the instruction cache is very small because, as we said before, all the threads are actually doing exactly the same and having the same instruction. And then we have some special function units for special math algorithms like sinus, for example, or square root. And those may be slow as well, and then taking a lot of time in order to complete. And in this time, we again will just put those threads away and get other threads to run. And the GPU is doing this for you, so you don't have to think about this. Okay, do all GPUs look like this? Basically, yes. But on the other hand, there's such a big zoo of different GPUs already on the market that it's sometimes pretty hard to understand what's really going on in the system that you're using. And at AMD we have all those different generations. At NVIDIA we have all those different generations. We have also different configurations for different applications. For example, the GeForce is usually used for gamer cards. Quadro is more for designers and architects. We have Tesla, which is only for computing and intended to be in servers. And we have Ion that is built for small devices like phones and so on. So we could have one of those cards, and they all could have one of those architectures. And then they could be even paired with a CPU, as we've seen before. And this boils down to a large variety of characteristics. So we could have a GPU that supports 512 threads, or we could have one that supports 1024 threads. We could have GPUs where you just have one kernel on the whole GPU, so one running program on the whole GPU. Or you could have one where 8 different kernels run. Or you could have one of the very modern ones where you could even have new kernels that are spawned on the GPU itself. You could have different sizes of registers, different sizes of this cache that you can configure. Sometimes it is configurable, sometimes it's not configurable. Some of the older cards only support single precision floating point, so if you read really accurate results, then you couldn't use them because you would need double precision floating point support, and this is only supported with the new cards. The old cards didn't have caches because they were graphics cards, basically. And the new cards, they have caches because they have this computation focus as well. And then they come with various amounts of cores, so you could have many cores or little cores. In notebooks, usually you have a very small amount of cores. In desktop computers, you have way more cores. The bandwidth varies, the frequency varies, and the frequency of the cores and the memory and the bus and so on. So you have all those different devices, and the question is how to program them. But before we're going to talk about programming, there's one special thing that I want to mention here as well, and this is Intel's Xeon Phi or MIG processor that we've been talking about before. So this is a special accelerator card that you can just build into your system. And this again has some variations to GPUs. So those are basically standard processors. A lot of standard processors, 16 standard processors. But still they are different from processors and have some features that are more GPU-like. First of all, they are pretty good with SIMD execution as well. So if you have data parallel programs, this Intel card can run them very good. As compared to non-data parallel problems, they will be really slow on this card as well, because the clock frequency for each of those 60 cores is not so high. But each of those cores can run 4 threads in parallel, 4 hardware threads, and you actually need to use this feature because after each instruction, the thread is changed. Okay, so if you have 4 instructions and you have 4 different threads, you cannot use the same thread for all the 4 instructions. And you have hardware support for adding, for example, 16 values to 16 other values, or multiplying 16 values with 16 other values. You always have those 16 elements and you have to work with those 16 elements. If you use another amount of elements, let's say you have your standard application and it just adds one value to another value, this is not very data parallel or SIMD oriented, then you won't get much speed up with this. So many of the rules that we are going to see for GPU accelerators apply here as well. And we're going to discuss this later. But apart from this, this is an accelerator where you can really have general purpose programs running on it. And it actually comes with a Linux that is booted on the system, that is running on the system. So it works by having this accelerator in your system, and then there's an operating system on the system, and you can connect with this operating system in your computer with your operating system, basically. And then both operating systems can talk to each other and share data. And the idea is usually to put your data there, execute a script there, get the result data, and then copy it back to your host system. So this is really what it will look like in the future. Maybe special accelerators even coming with their own operating system, and your computer can talk to them, or they will be more integrated into your system. We will see. But first of all, since we were talking about all those different ways that accelerators can look like, what would a programming model look like that can deal with this? Or how do you write your programs in a way that they will run on different accelerators in the future? We are going to look at this in the next lecture.